So, hmm, but the attendance is still very low. So I took the attendance sheet, download it. So I'm doing it. So I'm trying to see who are the consistently absent. So anyway, let's start. Now, can you see my screen and hear my voice? Okay. Okay. So now let's start. So what we were doing, we were basically reading the PMMC instruments. So that's what we were doing. And what we do in the last classes, that we try to find out that for a fixed amount of input or time invariant input, what will be the deflection. And we have calculated the deflection theta, which we will get from the PMMC instruments. And if it is not the pointer, if it is the light ray which get deflected on the screen or on the on the scale mounted 1 meter away from the wall of the wall where galvanometer is mounted, so you will get this type of deflection. So now one thing is very clear to all of you, that this instrument is very sensitive, because if very small amount of current passed, so you will get deflection. And when you will get deflection, that can be deflected as a pointer over scale, or that can be deflected as a mirror. And when you reflect some light on the mirror, that light can be deflected with some angle, and ultimately you can get the deflected light ray over the scale, and you can read the scale. So from either from reading in the pointer, which is in terms of theta, or the deflection over the scale, which is a d, small d, so you can calculate the current passed through in it, and that can be easily calibrated to other electrical parameter that will come later. So now the next question is, if your input is varying, or you give the fixed input, but before reaching to steady state, how the galvanometer will deflect, or the galvanometer, which is fixed in amount, and you wait for a long time, ultimately you will get the steady state, because you get some input which is not varying with time. But before reaching the steady state, it will go ups and downs and then reach the steady state. So before reaching the steady state, the time it passed and it deflects is called the transient. So for that we need to calculate the transient motion, and for that we need to calculate, just 1 minute, sorry. Okay, so now if you see that, sorry. So now if we want to know what will be the transient response, we need to know the transfer function of the instrument. For that, we need to see that what will be the different force acting on it when the instrument is moving. So now let's start with the damping torque. So we have seen the deflection torque, we have seen the restoring torque. Damping torque we avoided. Why we avoided? Because we say that our instrument is in steady state and there is no motion of the pointer, so there is no motion of the coils on the former. So damping torque we ignored. But now as we are trying to calculate the transient response, we cannot ignore the damping torque. So damping torque is also a kind of opposing force which will act when the instrument or when the former or when the coils on the formers are in motion. So suppose coils on the former are in motion, that means it has some velocity, and the force which will be proportional to the velocity will be the damping force, and it acts as a opposing force for which the deflection is created. So when the aluminum former moves with the coil in the field of permanent magnet, then what will happen? There may be some effect which will try to oppose the movement, and that opposing force will be proportional to the velocity. That can be caused, it is called the damping force. So there are mainly two types of damping what we discussed earlier. First is the eddy current damping, which is most predominating because it is on the magnetic field, some current carrying coils are moving, and another is air friction damping, which is not that much predominating, it's small amount. So now if we come to the equation of motions of a PMMC instrument, so or to know the transient response or to know the dynamic characteristics, we need to find out the transfer function of it. That's what I was always saying. So let's see how many torques are acting on it. Okay. So first is the inertial torque. What is that? Because of some current passed through the coil and it is inside the magnetic field, there will some force, and that force will move the former or will try to rotate the former. So that torque is due to the inertia of the moving system, so which you can call as the Ti inertia torque, which is J d2 theta dt2, where J is the momentum inertia of the moving system moving about the axis of rotation. So here the moving system is the aluminum former and the coil wound on it, and the aluminum former it rotates, and J is the moment of inertia when it rotates about the spindle, and theta is the deflection at any time t. Here theta is not the steady state deflection. Here theta is the deflection as a time at any time t. So you can write theta as a function of t also. Theta bracket t. In some book you see that they have written like that. Now what are the different force? Other different force. There is damping force. What is damping force? Damping is provided by the friction due to motion of the coil in the air. So damping is provided by the friction due to motion of the coil in the air, and also the electrical effects such as eddy current effect. So if a circuit is closed, some current will flow, and due to the eddy current effect, that damping torque will be produced, and damping torque will be proportional to the velocity of the moving system. So that is true for the electromagnetic damping as well as the air friction damping. So if you say that the damping torque is Td, then Td will be equals to D, where capital D is the damping constant, into d theta dt. Now there is another torque which will come into play, that is the controlling torque. So when you have some angle theta deflected and you have its deflection is happening over the spring, and spring has a spring constant K. So the controlling torque Tc will be the K into theta. So now if we combine all three, that inertia constant, damping constant, and control constant, so these three will act as a restored force. And then if you see the equation of motion, so now the torque balance you have to do. There are four torques. So on the moving system, first is the deflecting torque, which is Td, that is try to produce the deflection, and there are three other torques, which is inertia torque Ti, damping torque Td, and the controlling torque T0, which will try to restore the deflection, which will try not to happen the deflection. So at any point of time, this Ti plus Td plus T0 will be equals to T small d, which is the deflecting torque. So we can write the equation of motion as J d2 theta dt2 plus capital D d theta dt plus k theta will be equals to Gi. Now, if you see that when there is no theta is not a function of time, that means that there is no deflection happening, only the steady state condition is reached. Then you see that d2 theta dt2 and d theta dt all will vanish. You will get k theta equals to Gi and theta will be equals to k G by k into I, which is a steady state deflection. Now, as we are in the time varying motion and we are trying to observe the transient response or the output due to time varying input, so we have to write all those derivative terms with respect to theta. Now, if we can solve the equation 7.10, we will come to know what will be the theta as a function of time. That means at any point of time, what will be the reflection, we will come to know. So that is the case. So we have to solve the equation 7.10, and it is a second order differential equation, and all of you know that how you can solve a second order differential equation. There are two parts. One is the complementary function and one is the particular integral. Okay, so and the total solution will be the complementary function plus the particular integral. And if you see the auxiliary equation will be when you put right hand side 0. So from there, if you see that there are two roots, the roots are at minus t plus square root of d square minus 4kj by 2j, and another roots will be minus t, sorry, it will be minus, m2 is written wrong, it will be minus d minus root over d square minus 4kj by 2j. So these two are the roots, and now these roots can be imaginary complex conjugate and can be real also, can be left hand side, can be right hand side. And if you see that this d square minus 4kj, based on that you will get whether there is a complex conjugate root or there is no complex conjugate root. Based on that your response will vary. So now, as we have seen in the last chapter that, sorry, this one, as we have seen in the last chapter, that there are three cases which may arise. First case is the d square is less than 4kj. What does it mean? D square is less than 4kj. That means it is a imaginary, so you will get the complex conjugate pole. So m1 m2 are imaginary, and for this condition the motion is oscillatory. So one of you asked the question, when the motion will be oscillatory? The motion will be oscillatory when there is a complex conjugate poles, and that will can only happen when d square is less than 4kj. Now here you see d is the damping coefficient, k is the spring constant, and capital J, k is the spring constant and capital J is the moment of inertia. So all those things are in your hand because you are building you are designing the instrument. You know how much damping you can give, you know how what type of spring you will use, you know how much former J you have. So based on that you can know whether the d square will be less than 4kj or d square will be equals to 4kj and d square will be greater than 4kj. So as I discussed and told you many times that generally we prefer underdamped system. So m1 m2 must be imaginary, and the damping coefficients would be somehow in between 0.6 or 0.7. So in such a cases we need to design the d square which will be less than 4kj. So in such case you will get the such response. Now case 2, if you see that where the d square equals to 4kj, so they are the roots and the equal roots and not imaginary, real roots, and the roots are equal. So under this condition the galvanometer will act as a critically damped system and motion will be non-oscillatory, gradually rising still it reaches the final deflection. And case 3, when d square is greater than 4kj, in those cases both the roots are real and separated, not the same point, and the galvanometer is called as the overdamped condition, and this motion is non-oscillatory, and galvanometer will reach its final state very slowly after a long time. So based on these three conditions deflection, you will get the galvanometer what type of deflection you want. So now generally we prefer that a galvanometer to oscillate and come down to a steady state, which is a under damped condition, and based on that we design the galvanometer as the d square is less than 4 kg. Now as we design the galvanometer, we know the K, we know the J, we know all the parameters, so we can write a solution of this differential equation as a function of time for this case 1, case 2, case 3, and which is the case in your galvanometer. And for such a cases you can write the theta as a function of t, and you have seen what will be the expression. The same expression will come here, only you need to write the omega n and zeta in terms of d, k and j, and once you write that you will get the complete theta as a function of time, expression of theta as a function of time, and when you plot that you will see that ideally how your instrument should behave. So those expression I am avoiding because I already teach that on the last chapter, and but you need to read it from the Sahani. You please read it from the Sahani. They have given all the expression for all the 3 different cases, and you need to know that because in exam there may be some question that your D is such, K is such, this. You write that what will be the deflection at time t equals to this second. So for that you need to write the differential equation, you need to solve the differential equation, and then you need to substitute at t equals to that second to the differential equation so that you know the amplitude. Okay, so that is the case. Okay, let's see if any query. So I'm speaking long. Utkarsh is saying, can we in some vague sense claim that PMMC is a DC filter? Um, DC filter means what you mean to say DC filter? Can you little bit clarify? Okay, I got your question. So for that you need to understand. So what I am till now saying that if I give the step input, what will be the output? Now suppose if I give a time varying input, what will be the output? Suppose I gave a time varying input to a DC meter. Okay, for example, the AC current or something. So if this happens that it is changing very fast, and then the DC meter will try to follow the input, and but it has an inertia. So as a result, what will happen? It cannot give uh, the first thing is that in PMMC instrument, if you give the alternative current, sometimes it will be positive, sometimes it will be negative. So it will be try to deflect positive and then try to deflect negative, and then ultimately you will get the zero deflection. So that is the reason PMMC is not used for a particular. PMC is not used for alternating current. So it is for the uh, it is only for the direct current, DC current. Now the second thing is that if you give some thing which is not positive or negative, maybe always positive and trying to and fluctuating, then the output response whatever you will get, you can write it as a function of time, and but unfortunately you will not get that response if the input is varying very frequently, very quick variation. You will not get that output. That output follows the input because the inertia. So electrical parameters can change very fast, but as we have inertia, we have a former which is mechanical, we have a pointer which is a mechanical component that cannot change very fast. It has a point, it has an inertia. So for that it may show the average values. Okay, average values of the input it may show. That is true due to the mechanical nature of the instrument, so that it cannot show the fluctuations. But if you give the input positive and then negative, then positive negative like AC current So it will fluctuate around the zero, you will not get any reading. So that is what PMMC is on, only for a DC current or voltage. This is the first thing. Second thing, that if you are giving positive things which is fluctuating with time, the output cannot show such a cannot follow such input because it has the inertia. And for that, what you need to see, you may get the average value. Okay, that is true. Now let's go back to our discussion. So we have a permanent magnet moving coil. So three conditions are there. We can write the expression theta as a function of time, and whenever you want to know what will be the value of the output, you put that time, you will get the output. Now if you see now, then how our PMMC instrument is looking like. So it has a galvanometer coil. You see here, galvanometer coil is drawn. So it's wound on a former. It has a suspension. You see the suspension is there, and it has an external circuit attached with it. So it has some resistance. External resistance will be, and then it will be having some switch which you can close to measure the output current or output voltage, whatever it may be. It can be closed and then it can give the impulse, that means close and open, whatever may be. But the overall circuit will look like that. There is output circuit, there is external circuit with which a switch will be there. With that switch you connect, or with the wire you connect the galvanometer, and galvanometer will have some resistance R. Also external circuit will have some resistance R. And then you have the deflecting torque. You see the deflecting torque, and which is TD, which is GI. So deflecting torque is TD, which is GI, G multiplied by current I. So you have a suspension, and once a deflecting torque occurs, there are the restoring torques, three restoring torque. One is the inertia torque, because once the deflecting torque happen, the inertia come into play and it will oppose the deflection, and that will be J d to the dt. There will be damping torque, mainly due to the eddy current effect, which is capital D dt. There will be controlling torque, which will be due to the spring constant k theta. And at any point, these three will be equals to the deflecting torque, and ultimately you can solve the equation and you will get the output response. So that is what I want to say. So now you have seen that this is a second order system, and you know that your zeta can be calculated from the values of the spring constant Ga and the damping coefficient, and based on the zeta you will get what will be how your output will look like if you give any step input. So in that case, you will see that similar curve to the second order system. If zeta is zero, no damping, it will oscillate. Oscillation will not die down. If zeta is very small, the oscillation will be high. It will take time to die down. Then if zeta increases, the oscillation will be less. And if zeta is greater than 1, there will be no oscillation. It will always remain below the steady state. Okay. So this is the reason. Now there are few other issues we need to discuss. So now tell me if you have any query. So now till now what we discussed? We discussed the PMC instrument, its construction, and its static behavior. That means what will be the steady state output or theta, steady state output theta, its dynamic behavior, its transfer function, and then we are trying to discuss more. So you tell me if you have any other query. Okay, so then let's keep on discussing. Now this PMMC instrument, what we are telling that it has some damping. So total damping are what I discussed, that it is made up of two components. One is mechanical effect, one is electromagnetic effect. Okay, so mechanical effect is mainly air friction damping, because the former will move and former is hanging on the air. There is nothing attached with the former with coil, obviously. and the total damping torque will be the damping torque due to the mechanical behavior, damping torque due to the electrical is the eddy current effect. So there will be two damping coefficient. One is damping coefficient due to mechanical part, so that will be dm d theta dt, damping coefficient due to electrical part, that is de d theta dt, and that will be the overall two damping coefficient. So dm plus de will be d theta dt, and the overall damping will be dm plus de. Now, as I discussed earlier, that the mechanical damping component will be very small because it is on the air damping, and air has very less friction. So the damping is mainly due to the electrical effect, which is eddy current damping. So dm we can neglect. We can write this is equals to de d theta dt, which is the eddy current damping. Now, dE is the damping constant due to electromagnetic effect, and we can write that the damping constant will be equals to G square by R plus G square by N square RA. What is that? G square by R, G is the galvanometer constant. We know that that is proportional to the number of wound, that is proportional to the area of the former, that is proportional to the magnetic strength, and so on. That is the G, and the R, capital R, is the resistance of the galvanometer circuit when it is closed. That means it is the resistance of the galvanometer coil, which is wound on the former RG, and the external resistance RE, if any, and which is required for the damping. And now if you see G square by N square RF, so G square, we have seen what is G. N, capital N is the total number of wound. RF is the former resistance. Okay. So if we add these two, we will get the total damping constant. Now let's try to see what is the critical resistance. So the mechanical damping effects are very small, so compared to the electromagnetic damping, so we are ignoring that. So dm we can keep as 0. So we have d will be equals to de only, which is we have seen G square by R plus G square by N square RF. So damping due to the metal former is usually small, and we can put G square by N square RF equals to 0. So the main damping will be equals to G square by R. So damping coefficient will be mainly G square by R. Now for critically damped system, what will be the resistance R? So for critically damped system, we have seen that the damping coefficient D will be equals to 2 root over Kj. So now if you see that the damping coefficient, we can substitute it is G square by R will be equals to 2 root over Kj, or you can tell that it is taken such a way that 2 is coming, so that can be excluded also. So now you see that R, capital R, which is the critical damping resistance, will be G square by 2 root over Kj. So what is R? R is the summation of two resistance, which is Rg plus R, external resistance, for galvanometer coil resistance. And when that resistance will be equals to G square by 2 root over Kj, it will behave as the critically damped system. So the what I mean to say, the external resistance you can control so that the behavior of the galvanometer becomes the critically damped or over damped or under damped. Okay, because the damping coefficient depends on the resistance R, which is a galvanometer resistance, and the external resistance. Galvanometer resistance is generally fixed, and external resistance you can change so that you can operate the meter as a second order, as a critically damped system or over damped system or under damped system. Okay. Okay, so for the particular galvanometer for which G, J, K are constant, critically damped condition can be achieved properly by properly adjusting the value of the external resistance connected with the galvanometer. Okay, so external resistance connected with the galvanometer So we have seen that R, that means total resistance, will be G square by 2 root over Kj for a critically damped system. Now we know that we know the galvanometer resistance Rg, and R is the sum of galvanometer resistance plus external resistance. So the amount of external resistance you have to apply so that the galvanometer works as a critically damped system, that will be G square by 2 root over Kj minus the galvanometer resistance you have to subtract, and that much amount of external resistance you need to apply so that this galvanometer acts as a critically damped system. Okay. Now let's see if there is any query. Yeah, you can ask question if you have any. Okay. So if there is no question, please let's follow the discussion. So now there are two major issues we need to discuss. That is the sensitivity of the galvanometer. I said that sensitivity of the galvanometer is generally very high. So that it is very sensitive instrument. It can excuse me. It can detect a very small amount of current, even a small amount of charge. When it passed, it can detect very quickly. So its sensitivity is high. So still we need to know the expression of the sensitivity. So the sensitivity of a galvanometer may be defined in a several way. So there are various types of sensitivity. For example, current sensitivity or voltage sensitivity or mega ohm sensitivity. We'll discuss one by one. So what is current sensitivity? Current sensitivity of a galvanometer is defined as the deflection produced by unit current. So if the deflection, steady state deflection is theta F, and the current for which the current I, so we have the current sensitivity SI will be equals to theta F by I. But we know that the current theta F will be equals to GI by K. So the current sensitivity will be GI by K into 1 by I. So which will be equals to G by K, because I will cancel. That's what I was telling, that G by K, and G will be equals to, G is the galvanometer constant as I discussed, which is proportional to the number of turn, which is proportional to the area, which is proportional to the area of the former, which is proportional to the magnetic strength, and K is the spring constant. So you see that in practically the G by K is the current sensitivity. So the current involved for so to get the high current sensitivity is always we want highly sensitive instrument. So to get the high current sensitivity high, we need to have more G and we need to have small K. So if we want more G, so we can have more number of wound. N, we can have the former area more. We can have the more. We can have the more number of turns. We can have the strong magnetic. We can have the strong magnetic B magnetic field. So if we can increase those things, our sensitivity will increase because we'll get more deflection. And now K is our the spring constant. So if we have the spring constant very less, so then the restoring force will be small. So we'll get more deflection for the same current. So the sensitivity will increase. So in practice, the currents involved are very small for galvanometer. So because you know that the former on which the wound is made is a uh, not very wide, and if it is not very wide, you need to make many wounds on it. So if you want to make many wounds on it, you need to take a very small thin wires. So in such cases, if you take thin wires, the large amount of current you cannot pass, because if you pass a large amount of current through the thin wire, what will happen? You know that thin wire will get heated and it will ultimately burn. So you need to pass a small amount of current. If there is large amount of current in the circuit, what you have to do? You have to make a shunt so that the most of the current passes out of the galvanometer and a small fraction of the current passes through the galvanometer. Very small fraction of current passes through the galvanometer, which is very small. Because one thing you have to remember, this PMMC instrument cannot sustain very large amount of current. Okay, so but in lab you may see that very large amount of current you are giving to PMMC instrument and it is giving deflection. That is true, but there is the shunting mechanism which we will read later, so which is inbuilt inside those device. So what will happen if you even give the very high amount of current, say 10 ampere, 100 ampere, 500 amperes, so the most of the currents, the shunting is done such a way that most of the current will pass through the shunt and very small amount of current in the order of milliampere or so will pass only through the uh, galvanometer. Because the reason, you know, that that galvanometer consists of a very on the former, which is on the uh, you know, wounds, which is on the former length and breadth is not high, and you need to have many turns, and to do that you need to have very thin wire, and thin wire can carry only small currents. Okay, and it is good in the sense that you don't need to take current from the circuit, which is also very good. Only a small portion of current, you shunt it, take it, and then you get deflection out of that current. So now the thing is, this is due to this current sensitivity equation 7.75. It is due to the deflection over the pointer. Now there are another types of galvanometer which I said, which is mounted on wall. There is a mirror. When mirror is deflected, you get a deflection of light, reflected light on the scales, which is small d. So in such a cases, the current sensitivity will be SI will be equals to small d, which is the deflection of the light divided by the scale division. Okay, so I into 10 to the power 6. So here you see that I is the current in ampere, small d is the deflection on the deflection in scale division, and you have the current sensitivity, and unit you see it is millimeter per microampere, so it is so much sensitive. Okay, the scale is usually kept 1 millimeter division, so scale is generally 1 millimeter division, not less than that, and it is placed 1 meter away from the galvanometer. So the current sensitivity we can write small d by I into 10 to the power 6. 10 to the power 6 is coming because this is from the um, very long distance, 1 meter distance, 1 meter distance. Okay, so the current sensitivity will be d by I into 10 to the power 6. So if you see that I by d, which is the I by d will be equals to k by 200g. How you are getting k by 200g? Because you can use the equation 7.6, which is SI will be equals to d by I into 7. So this is I by d equals to k by g. How you are getting? So the current sensitivity SI you can substitute there, which is k by g. So if you substitute k by g, so I by d will be k by g into 200. So what you are getting, SI will be equals to, so from 200 g by k into 10 to the power 6, so 5g by 500k something. So here also you see that sensitivity is proportional to g by k. Here you have seen sensitivity is the g by k. Here also you have seen the sensitivity is proportional to g by k. So this is current sensitivity. Now let's come to voltage sensitivity. So what is voltage? So current sensitivity, what was the meaning of the current sensitivity? So meaning of the current sensitivity is that the amount of deflection which is produced due to the deflection which is produced when the unit current is passed. So now the voltage sensitivity, similarly we can define the voltage sensitivity which is the deflection in scale uh, per unit of voltage applied on the galvanometer. So voltage sensitivity is defined as SV, which is scale division per unit voltage. So which will be equal to small d by I into Rg into 10 to the power 6, which is the voltage sensitivity. So for galvanometer, which is 1 meter away from, so 10 to the power 6 is coming, you know how it is coming, because of microvolt. You see the scale division per microvolt. If microvolt is not there, scale division per volt 10 to the power 6 will not come. But generally I said that it is very sensitive instrument. So you very small amount of voltage will produce. So to change the unit in the microvolt, 10 to the power 6 is coming. For a galvanometer with scale 1 meter away and with the one scale division 1 millimeter, the same thing will come. It will be SV will be equals to G by 500K into RG. So this is the case. Now there is another thing which is Megom sensitivity. Megom sensitivity is the when we want to measure the resistance with the help of the circuit, galvanometer circuit. So then the Megom sensitivity come into play. So this is the deflection in scale for 1 megom, and as the coil resistance is negligible, we can say that megom sensitivity equals to S0 equals to resistance in megom to give a deflection of 1 scale division with 1 volt, which will be D by I into 10 to the power 6, which is the megom per scale. So the galvanometer with scale 1 meter away similarly will get G by 500K. So whatever be the case, always you see that you are getting something G by K. So whatever be, whether it is the voltage sensitivity, current sensitivity, or megom sensitivity, what basically to get the more sensitive voltmeter, you need to increase the value of G. Maybe that is discussing. Yeah. So whatever the sensitivity it may be, you will see that always it is G by K ratio. So to do so, you need to increase. If you want more sensitive instrument, you need to increase G. So if you want to increase G, you need to increase the former area. You need to increase the number of turns. You need to increase the number of turns, and you need to increase the magnetic strength. So if you can increase those, your sensitivity will increase, and on the other hand, if you can decrease the spring constant, your sensitivity will always decrease. So sensitivity is the one which produces large deflection for a small amount of current. So for that, you need to have a large deflection. For that, you need to have very high G and small k. So thus the value of SI should be large in order to get galvanometer more sensitive. Hence, for a sensitive galvanometer, the displacement constant G or galvanometer constant should be large, and the control constant K, not S, it is wrongly written. Control constant K should be small. So now the displacement constant, we know it is NBA. N is the number of turn, B is the strength of the magnetic field, A is the area of the former. So therefore, for sensitivity to increase, we can increase the number of turns using the high flux number of turns and using a high flux density magnet. And for a given area of the former and a constant value of flux or B, the displacement G can be increased by increasing the number of turns. So if the winding area is fixed, that means the former area is fixed, a number of turns can only be owned if we use thin wire. That is what I was telling. So thus to increase the sensitivity of the galvanometer, winding coil, large number of turns are used, and for that we use a very thin wire or fine wire. Hence, for a sensitive galvanometer, those wires are very thin, and the values of the resistance of the coil is, it is not, it is large. RG is large, comparatively large. Large, that you don't think that it is a mega ohm or something. It is in the order of ohm or even less, but comparatively large. So we can increase the sensitivity also by making the control constant K small. Thus, a suspension of small stiffness or the small spring constant leads the increased sensitivity. Okay, now let's see if everything is fine. Okay, there is no. Now let's see, there are, as I discussed, I put it on the slide that there are mainly three types of galvanometer. In fact, you can think about there are two types of galvanometers. So DC galvanometers, PMMC instruments and galvanometers, they are made for DC measurement, not AC. That's what repeatedly I was telling. And there are three types of, one is portable type. They are small instrument, similar in construction to other types of portable instrument. They may be pivoted, so pivoted, or may have the taut suspension. Okay, so these types of portable galvanometer, you will see all the meters, DC meters we have in our machine labs. Those are this type of galvanometer. And laboratory reflecting type, this is not a portable type, but this is very sensitive, and we use to mount it on the laboratory. You might have seen this in physics lab, that with the mirror and the reflecting light and all. So they are mounted on the wall. They are highly sensitive, they are very much sensitive compared to portable type. They are highly sensitive, but they cannot, you cannot carry it to some place where you want to measure it. You cannot just attach the wires, keep it on the table. It is not. You have to make the, you have to suspend it on the wall. You have a mirror, you have a light reflecting, you have a scale where you will see. But on the return, you will get very, it is a very high sensitive instrument. Even if some charge passes, it will reflect a lot. Another type is the box type. So the box type instrument, they use the taut suspension, and they don't need the leveling. The box uses the taut suspension, and it includes the complete optical system, and therefore it is not necessary to make separate mounting for the galvanometer, lamp and scale, all those things. Okay, it comes with the complete, in the inside the box it comes with the optical system, reflection, everything. And it is a taut suspension. There is no need to make label it when you install, and everything comes and inside the box. Mostly these first one and two types instrument we use, that portable type instrument that every day you use. And in physics lab, that reflecting type of galvanometer you use, D'Arsonval galvanometer, and so for very sensitive measurement. So that's what I was telling from the beginning. So I put it on the slide so that it will be beneficial for you. Now let's see if you have any query or anything. Okay. So now take some rest, maybe 5-6 minutes. After that, I will join. In the meantime, if you have any query, you can ask me, or otherwise, let's take some break. And after that, again, I will join and take one more class. Okay. Thank you.